So, dear colleagues, as the President, I have the great pleasure of moderating this third general lecture talk. And we are very happy, and it's my pleasure to welcome a distinguished Professor Nan Chi from Fudan University, where she's a professor and also executive dean of the College of Future Information Technology. She has her academic degrees from the Beijing University of Posts and Telecommunication, is very active scholar in the field of optical fiber communications and visible light communication, optical packet switching, and so on. Has received many awards like the National Science Fund for Distinguished Young Scholars, the New Century Excellent Talents Award from the Education Ministry of China, Shanghai Shuguang Scholarship. She's a fellow of the Optical Society of America, nowadays called Optica. So please join me on welcoming Professor Nan.
Okay, thank you, Chairman. Good morning, ladies and gentlemen. It's my great honor to join the URSI conference. And just now, as I mentioned before, the URSI is a very famous worldwide organization, and it's my pleasure to share our latest research in intelligent new spectrum communication towards 6G. Well, before my presentation, I would like to show you this slide. This slide is about 2 Nobel Prizes. The first one is Marconi. Mr. Marconi won the Nobel Prize in Physics in 1909 due to in recognition of their contributions to the development of wireless telegraphy. And the second one is from Dr. Charles Quinn-Gao. He won the Nobel Prize in Physics in 1909 for groundbreaking achievements concerning the transmission of light in fibers for optical communication. So from wireless communication to optical communication, the history spans over 100 years. So I'm optical people. I think wireless communication and optical communication, the convergence of this wireless communication and optical communication is the topic of my talk today. Here is the outline. First, I will give you a brief introduction of what is 6G and what we are doing in 6G. And then I will give you some introduction on terahertz communication, visible light communication, and optical interconnect. And in the end, it's a future perspective. Okay, this picture shows the 5G. At the end of last year, in 2024, 5G commercial services have been officially launched by more than 300 operators in more than 100 countries. And while more than 500 operators are investing in 6G network through testing, verification, and deployment planning. In June 2023, ITU released the recommendation on the framework and overall objective for IMT 2030 and future development. From this picture, we can see 6G expands 3 major scenarios compared to 5G, that is, integrated sensing and communication, integrated AI and communication, and ubiquitous connectivity. I think 6G will contribute towards the global forefront of science and technology. It will develop next-generation communication technologies, including core devices, architecture, and techniques to establish 6G optical and wireless integration. And it also will address major national needs and the national economy. It with scarce wireless spectrum resources, 6G aims to achieve a 1,000-fold increase in capacity, laying the foundation for national informatization. This slide is courtesy by China Telecom. It tells us the main trend in 6G development. There are two branches. One branch is to build up channel theory to unlock the potential of spectrum and the spatial domains, including spectrum fusion, ultramassive MIMO, and reconfigurable intelligence surface. The other branch is multi-domain convergence technology, enables innovative fusion across new dimensions, including cloud network convergence, space-ground integration, intelligence network convergence, and integrated sensing and communication. So what is the most important feature for 6G? I think maybe the requirement of bandwidth can be more 1,000 times of 5G. People are always doubting about why we need such high capacity, because human perception has its upper limit. Should we need such high capacity? But after the emergence of ChatGPT, network capacity has grown at a rate of 100 times in 2 years. So no one questioned about such massive capacity demands. But the question is, how can we achieve this target? Because 2G, 3G, 4G, and 5G has exhausted the radio frequency. People have to look at ultra-high frequency domain, that is terahertz communication, visible light communication, infrared communication, and ultraviolet communication. Another important feature is ubiquitous connectivity, that is non-terrestrial network. 6G provides superior coverage by integrating space, air, underwater network with terrestrial network. Let's move to terahertz communication. The terahertz frequency is around 0.1 terahertz to 10 terahertz. The wavelength is from 3 millimeter to 0.03 millimeter. Terahertz is just located in between electronics and photonics. It is the rotational and vibrational frequencies of all macromolecules, so making it very relevant for applications in electronics, in information, life sciences, defense, aerospace, and many other fields. There are two ways for terahertz generation. One way is based on solid-state electronic emission and reception. The other way is based on millimeter wave terahertz emission and reception on photonic technology. That means we use two optical wavelengths and we beating them together. The frequency difference will be terahertz. So people from wireless communication will do frequency doubling and frequency tripling to generate terahertz frequency. And people from optical field will do this beating technology. So what we are doing is fiber wireless integrated, millimeter wave, terahertz wave 6G wireless access. And it can provide 3 directions. The first is fiber wireless integration. It can provide significantly extended coverage. And second one is photonic assistant terahertz generation. It has extremely high frequency. And third one is optical signal processing. It has exceptional large bandwidth. This picture shows our National Natural Science Foundation supported project. The name is Optoelectronic Coverage and Integration for Terahertz Communication Towards 6G. We can see there is a central unit and fiber network and base station. And after base station, the signal is transmitted over terahertz wavelengths. So in this project, we have 2 key components. One component is to realize optical to terahertz conversion. We can realize ultra-wideband, high-efficiency photodetector. And the other one is ultra-high speed and low voltage lithium niobate on insulator modulation. It can realize terahertz to optical conversion. So this is our latest achievements on D-band MUTC, that is modified uni-traveling conversion photodetector for fiber terahertz integrated communication system. And these devices, we can realize terahertz data rate up to 160 gigabits in the 110 and 170 gigahertz range. Also, we have done some experimental demonstration on broadband microwave photonic processor based on Mach-Zehnder interferometer weight bank for radio frequency blind interference cancellation. It can provide flight transmission response. It can provide wide working bandwidth and very strong robustness to environmental changes. Because it's strong linear controllability, it has very strong optical and terahertz manipulations. And in this way, we can operate in frequency range over 20 gigahertz and over 6G baud for 16 QAM modulation format for radio frequency signal. This is our demonstration for high-capacity terahertz MIMO multiplexing. In this experiment, we use MIMO antenna, 4 output antenna and 4 input antenna, and we can achieve a line rate up to 475 gigabit per second in G-band, that is more than 200 gigahertz, and this test result has been submitted to IMT 2030. We have also tried field trial. This is a field trial demonstration between our 2 campuses, Handan campus and Jiangwan campus. The transmission distance is more than 4.6 kilometers, and we use W-band, that is 100 gigahertz millimeter wave communication, and we can realize 6 gigabit per second at 8 AP-RASC modulation, 50 gigabit per second at QPSK modulation, and 40 gigabit per second at 16 QAM modulation. Clearly, we can see when you increase your modulation order, and the data rate will be decreased due to the whole system nonlinearity. This is our long-distance, ultra-long-distance demonstration for photonic terahertz communication. It has Lianyungang at sea side. We transmit over the sea surface more than 30 kilometers. And this is a full photonic up and down conversion with line rate and distance product of more than 800 gigabits per second kilometer. This is a record for rate distance product, and it's a post-deadline paper in last year, OFC 2024. Okay, so much for terahertz communication. Next, I will talk about visible light communication. So what is visible light? That is a light we can see by human eye. The frequency is from 400 terahertz to 800 terahertz, and the wavelength is 380 nanometer to 760 nanometer. Visible light spectrum is an unexplored terrestrial for humans, and it can activate bandwidth resources up to 400 terahertz. So how about 400 terahertz? We just see in fiber optical communication, our bandwidth is only 5 terahertz. So it's 8 times than fiber communication. It can provide very large bandwidth. The advantages of using visible light communication in space communication, because the wavelength of visible light is shorter than fiber communication. In fiber communication, we usually use 1550, and in visible light communication, we use green and blue light. The blue light is 450 nanometer, and as we can see from laser mechanism, and the shorter wavelength has a better beam quality, which means it has lower wavelength means smaller divergence angle, and then we can transmit a longer distance, for example, to Moon and to Mars. And the other advantages is in anti-radiation, because visible light devices is based on gallium nitride. This is a wideband semiconductor devices. It's 1,000 times higher tolerance to the radiation intensity compared to traditional infrared optical fiber laser sources. The other advantage is for visible light is in underwater communication. Usually, there are 3 different methods to realize underwater communication: acoustic, radio frequency, and visible light communication. By using acoustic communication, the transmission distance is very long, maybe more than 1 kilometer, 1,000 kilometers, but the transmission speed is quite low. For radio frequency, because the radio frequency has very strong transmission loss due to the conductivity in seawater, it's a skin surface, skin effect. So it has very short distance. Visible light communication may be the only way to realize very high-speed underwater communication in medium transmission distance. This picture shows the configuration of visible light communication. It is similar to all kinds of communication methods. There is transmitters and there is receivers. In transmitter, we can do coding, modulation, and pre-equalization. In receiver, we can do decoding, demodulation, and post-equalization. We summarize the research into 4 different categories. The first one is materials and devices. There is LED and photodetector and laser diode and modulator, amplifier, and PLC. And the second one is modulation technologies. We can try different modulation technologies. For example, carrierless amplitude modulation and bit loading, DMT, OFDM, single carrier FDE, and THB, NLTCP different coding method. And third one is signal processing for post-equalization, pre-equalization, blend equalization, and some nonlinear compensation method, and also some signal processing method based on artificial intelligence. And the third one, the last one is multiplexing and networking, because we have to build our network for MIMO network, for NOMA network, and for Li-Fi network, and also we can combine wireless communication network with optical communication network. We can build a heterogeneous convergence network. About the key components in high-speed visible light communication. For the transmitter, we have 3 different choices. The first one is laser. The first one is LED. The LED has spontaneous emission, and it has narrower bandwidth, but it has wider coverage range. And also we can use laser diode, but we need alignment. For laser diode, it has higher bandwidth. And between LED and laser diode, that is a superluminescence laser diode, it's the characteristics of such kind of devices. It has benefits from LED and also the advantages from laser. About the receiver technologies, a very simple way is to use a PLN photodetector. We can convert optical signal to electrical signal. And to further increase our receiver sensitivity, we can use APD detector. Of course, we can use image sensor, for example, CCD or CMOS, but at very low frame speed. And also, we can use some single photo detector for quantum communication and for ultra-long distance communication in underwater and in deep space communication. This is a very interesting devices. This is a joint collaboration work with Nan Chi University. It's a silicon substrate LED, and this LED can increase light extraction efficiency because it has hemispherical and pyramidal pattern surface textured on this gallium nitride LED. So it can increase the light extraction efficiency, and it has Argentine reflector and this reflector is used to improve single-side luminescence. To improve the available bandwidth of conventional LED devices, and we design and fabricate and integrated this multicolor LED visible light communication system with WDM method. And the system uses a silicon substrate gallium nitride-based LED with a 3D structured quantum well. You can see it's a repeat quantum well, and we can increase carrier injection and recombination efficiency. Based on this kind of integrated 4x4 LED array, we can achieve more than 30 gigabit per second transmission rate on a single chip. And this multicolor LED array contains 8 different wavelengths from 450 nanometer to 660 nanometer. And the whole system achieved an overall data rate of 31.38 gigabit per second data rate. And the most significant improvement appears in the yellow and the green wavelengths. We also fabricated some high-speed laser diode. This is a downscaling and doping profile for high-speed mini laser diode. We designed a very narrow range waveguide. The diameter, the length is only 2 micrometer, and we have this super lattice multiple quantum well structure and can restrain the relaxation in lower wavelengths, in lower waveguide. So the light confinement is very good for these devices, and then we can increase the light response and increase our bandwidth. By using this ultra-high-speed blue gallium nitride semiconductor LED, we can realize very high-speed visible light communication. And in this experiment, the wavelength is 451 nanometers, so it's a blue laser diode. The 3 dB modulation bandwidth is 5.9 gigahertz, and we use bit loading DMT modulation. The total data rate is more than 20 gigabit per second. And this is our latest result. We have this band structure engineering for high-speed indium gallium nitride-based mini LED devices. The 3 dB bandwidth is more than 8.4 gigahertz, and the total data rate is 36.5 gigabit per second. Usually, when we detect a visible light signal, we use silicon-based detector. The silicon-based detector has some short disadvantages in blue and green wavelengths because relatively lower responsivity. So the transmitter is based on gallium nitride. Why we use such kind of devices for photodetector? So we designed this micro photodetector in gallium nitride, and we can achieve 10 gigabit high-speed visible light communication. And this is the first time gallium nitride photodetector can achieve more than 10G data rate. This is our latest result. We can achieve gallium nitride micro PD exceeds 15 gigabit per second communication. This is also very interesting experiment. Usually when we do optical transmission, we always thinking about alignment problem, about the coverage, the field of view problem. And in this experiment, we integrated a 4x4 PD array. Then we can detect the signal from different directions. And then we can combine the signal from different directions. We detect them simultaneously. And then we can realize very, very flexible detection by this integrated parallel gallium nitride, indium gallium nitride micro photodetector array module. This is our experimental setup, and by using this Hoffman coding method, the system can simultaneously receive 2 independent signals and flexibly adapt to the channel. And the system has a bandwidth of 2 by 2 gigahertz, 2.2 gigahertz with combined net data rates of 2 channels reaching up to 12.27 gigabits per second. We have also done a very interesting experiment for flexible detector. This is a wearable health monitoring, and this device is based on perovskite, so it's very soft and it's very flexible. And this device is self-powered devices, so it has very low power consumption. And we realized these wearable devices, and we entangle these devices in arm, and we can do some medical purpose, such as heart beating monitoring. Also, some demonstration for underwater communication. And in this experiment, we integrated monolithically 5 different lambda wavelengths transmitter module, and we use WDM and PDM technology, and we can achieve a data rate of more than 170 gigabits per second, and it's 16 gigabits higher than the traditional water and LMS algorithm, and we transmit over 1.2 meter water tank, so it is an underwater demonstration. And also about the long distance transmission, we have tried transmission length at 100 meter. In this transmission length, we can achieve 47 gigabits per second, ultra high speed, free space, visible light, tricolor laser communication system utilizing time domain Hoffman hybrid coding. And the tricolor laser achieve the highest distance rate per duct, 4,705 gigabits per second per meter. And this experiment demonstrates that visible light communication system has great potential in long-distance, high-speed transmission scenario. And this is a field trial for visible light communication, more than 8 kilometer field trial, and data rate is more than 7.6 gigabits per second, yielding a maximum distance rate per duct of 61 gigabits per second per kilometer. We have also done some research in this meta-surface. This is meta-surface-based full-color circular anti-focusing Airy beam transmitter. As we all know, basal beam or Airy beam has self-healing characteristics. So we can transmit an Airy beam for underwater environment when there is a bubble, when there is turbulence, obstacles, and the beam can passing through this bubble and heal together itself, and then self-healing, and then we can get a good detection based on such kind of basal beam. And we design a wideband meta-surface devices. These devices can be used for our self-designed, self-fabricated tricolor laser. And this shows the experimental result. And in this result, by using this wideband meta-surface lens, and after passing through 3 tricolor lasers, and we can realize 91% data rate improvement and achieving reliable 4K video transmission in turbulent water channel, and the relatively transmission distance is 100 meter underwater transmission. Okay. So the next one is optical interconnections. The AI era is witnessing a sharp rising in interconnect capacity requirements for intelligence computing networks in data center. And this urgently calls for adoption of scale-up and scale-out network expansion technologies to meet the rapidly increased demands. So what is scale-out and what is scale-up? Scale-out means expanding the system by adding more computing nodes to achieve higher computation power, which means more servers. Scale up means enhancing the system performance by increasing the computing power of a single node. So more GPUs within a single server. So scale up and scale out. All this build a cluster network in artificial intelligence data center. This is a collaboration experiment with Tsinghua University in Luo Yi professors group. It's micro-LED optical interconnect array chip. We use high bandwidth 2x2 micro-LEDs and 2x2 PD arrays, and we use imaging fiber, so we can realize OOK modulation at 12 gigabit per second and DMT modulation at 15 gigabit per second. Also, we have built this 100 gigabit visible light laser communication prototype. We use 10 different wavelengths, and we can realize 110 gigabit per second for optical interconnect based on visible light laser communication. So this is a prototype, and this is another prototype for high-speed optical interconnection in data center. That is 500 gigabit visible light communication. We use 5 different wavelengths, and the total data rate is 519 gigabit per second, and this one is OFC 2024 top-scored paper. And this is a very interesting experiment for programmable optical switching. So we use optical interconnection. We also use optical switching between different GPUs, CPUs, and between different data centers. And in this experiment, the existing visible light-based optical interconnection architectures preliminarily rely on fixed and point-to-point link. And in this experiment, we use SLM, and we can use programmable, and we use a physics-inspired forward-backward two-stage network, that is AI signal processing method, to achieve efficient light field pre-manipulation, and we can enable flexible and programmable visible light optical switching. This is our experimental result. We can achieve unicast switching. We can also achieve multicast switching. For unicast switching scheme, the efficiency is around 0.99, and the average multicast efficiency is more than 0.9. The average data rate is around 14 gigabit per second for 3 lambda 6 different channels of optical interconnection, and the maximum throughput for this programmable optical switching can reach 629 gigabit per second. In optical interconnection, we use different devices. For example, we need high-speed optical modulators, and this is a demonstration for silicon-based micro-ring high-speed modulator. And this is a micro-ring modulator, and we can realize 240 gigabit palm modulation. Further, we increase our signal processing algorithm. We use a BIGRU, that is AI accelerated algorithm, and then we can obtain data rates of 300 gigabits by using this micro-ring modulator. Also, this is our latest result, a thin-film lithium niobate Mach-Zehnder modulator. We can realize single wavelengths, more than 40G transmission. And the baud rate is 128 gig baud rate, and we use Palm 20. And also, we have tried the multi-dimensional multiplexing optical interconnect. We propose a high-capacity on-chip optical interconnect architecture based on spatial temporal frequency multi-dimension multiplexing using inverse design devices. For traditional photonic integrated devices, the device's size is usually very large. It's micrometer devices. And in this fabrication, we use inverse design, so we can use sub-wavelength design and sub-wavelength devices in nanometer scale. And we realize 5 different optical mode, and we have 88 wavelengths. The result is 440 parallel transmission channel, and all integrated onto a single photonic chip. And finally, we get a total spectrum efficiency of 8.68 bits per second per hertz, and the total net data rate is 38 terabits per second. So this optical interconnection can realize more than 38 terahertz connection. So in conclusion, I will talking about some words on future perspective. 6G technologies will be focused on different areas. In China, there are 3 major operators: China Telecom, China Unicom, and China Mobile. People are interested in non-terrestrial network and self-MIMO and rays and new spectrum, terahertz, and visible light communication. European and American operators such as ATT, BT, and VDF, they are interested in NTF, MIMO, rays, and also new spectrum. And in Japanese and Korea operators such as NTT, SKT, or KDDI, they are interested in NTN and MIMO rays and telecom large model, and also new spectrum, terahertz, and centimeter wavelengths. So looking into the future, I think the advances in optical electronic integration technology can promote the development of new spectrum communications. It has a lower power consumption and a compact device size, and promising advances in millimeter wave and visible light communication. So for terahertz communication, I think the on-chip terahertz signal processing will be a very promising research directions. And with the development of ultra-high bandwidth modulators, photodetectors, we can achieve on-chip terahertz signal processing. And the microwave photonics or terahertz wave photonics can realize faster, smaller, and more efficient terahertz technologies. About visible light, we have to try different material. In visible light, there are different kinds of material. It's different to 1550 C-band optical signal. For example, gallium nitride. For example, silicon nitride and lithium niobate devices. It can span the visible light range, and it has very good optoelectronic characteristics. So it can provide superior nonlinear properties and demonstrating greater potential for photonic modulation. So when people talking about 4G, we think 4G connecting people, 5G connecting things, and for 6G connecting intelligence. So the 6G development vision is from connecting people to things to connecting intelligence. The last slide. I'm people doing optical communication, but wireless communication and optical communication are 2 dominant parts in communication field. I think people have to working together to support 6G development. The key words in demand development is ultra-high speed, ultra-large capacity, bandwidth, coverage, and ultra-large connectivity, and ultra-low latency. And the key words in technology development, that is new spectrum, spectrum efficiency, seamless integration, perception, and native intelligence. looking into the future, optical people and wireless people will working together to advance the process of future 6G communication. So much for my talk. Thank you for your attention.
Thank you very much, Professor Chi. This is systematic presentation about the demands of the sixth generation communication technology and terahertz and optical communication systems. So we have time for questions and comments, so feel free to raise questions. Yes, please. Please use the microphone.
Very interesting work and talk. So just one question about the underwater communication. The medium, the channel is still restrictive, right? Like, so are there any ideas to overcome those?
Okay, yes, that is a very good question because the transmission loss for underwater channel is very large. Usually people can realize underwater optical transmission within 100 meters. But our recent result in South Sea in China, because the water quality is very good, so we can realize 300 meter underwater transmission. I think later when we have good optical resources and single photon detector and single photon detector array, maybe we can imagine 500 meter underwater communication, but it's still very short compared to acoustic communication. And I think maybe we can use a network, we can use relay and to increase the transmission distance. Thank you.
Yeah, the underwater is certainly then different in clean lakes and then salty ocean and so on.
Yes, for harbor water, it's too dirty, so the distance is only about 10 meters, you know. Yeah.
But then in a clear Finnish lake, you can see 10 meters down very easily, so the lake is not so. But one thing, in one of the last slides, you showed the Chinese, the European, American, Japanese operators' interests. But did I understand correctly that this visible light communication is only happening in China, not in other parts of the world? Because I didn't see the visible light communication listed in the European or American or Japanese operators' wish list.
Okay. Well, I think in Japanese and Korean people, also in UK, people are very interested. For example, there are people in Oxford University and Cambridge University, Edinburgh University, and Strathclyde, Glasgow University. The professors are doing visible light communication.
But that is then more academic things.
Yes. The operators in Japanese, in Japan and in Korea, they are looking for visible light navigation and positioning method to do that. But I think in China, we change our group name for 6G because we have a discussion group, a standard group in 6G in China. Previous name is visible light communication, but currently the name is optical wireless communication. We are looking for inter-satellite and satellite ground communication based on laser. So it's optical wireless communication.
Right.
So it's very useful. Yeah.
So instead of Wi-Fi, we have Li-Fi.
Yes, but also optical wireless communication.
Okay.
Yeah, free space optical communication.
When I see those big demands of 6G that you said there, ultra high, ultra large, ultra strong things, so it means that then these lasers that transmit light. So if we replace the Wi-Fi here with the lasers, so is that dangerous for the eye? Because if we can see that, because that is visible light.
Yes, that is a very good question. I think this is a contradiction, I think, for the LEDs and lasers. For LED, it's safe for human eyes because it's spontaneous emission and the light density is smaller. So, and people can see the light. Yeah. So there's no harm to human eye. But for laser, because the light density is large, so it may harm to human eye. But currently, we are talking about the optical interconnection in data center. So there is a strong demand in this area because the the market demand is 1.6 terabit per second for data center optical interconnection. But currently, our product is only 800 gigabit per. So people are doing a lot of work in this area.
I see. Yeah. Any other question? Yes. Yes.
This again, it's a standard problem for the community, but your thoughts on, is there any way to integrate the solid-state sources with the optical counterparts? Because the solid-state sources have advantages of high power for the terahertz, but most of your work is based on optical domain, like as you mentioned, like it's a millimeter wave technology which you're expanding it. So is there any way to fusion the two, take the solid-state sources and do it in the photonic technologies?
Sorry, I'm not quite understand. It's
in the terahertz?
The sources for terahertz transmission, you mean?
Oh, terahertz, the sources for terahertz transmission and for optical transmission. Yes, I think there is a main problem because we have very strong microelectronics. People design multiple layer microelectronic circuit, so it's very mature design. But for optical design, we only have 2D design. It's planar optical circuit. So how can we realize 2.5 dimension integration and 3D dimension integration? I think is a big challenge. But I think currently flip bonding may be a reasonable way to realize optical and electronic integration.
Thank you.
Yes, indeed. I mean, I have the respect for telecommunication engineers and signal processing things because you showed something that you can take 8 bits per second per hertz. So I thought that if there is a bandwidth of hertz, you can only use one bit per second, but obviously with complex modulation systems, you can go so high. Yeah.
Yes, I think the one way is to increase signal-to-noise ratio. When you increase your signal-to-noise ratio, you can realize high-order modulation format, which means in single baud, you can transmit multiple levels. And I think the other way is for linearity. You have to realize very good linear devices for this. And a third way is optical mode. We have different LG mode, HG mode, different OEM mode, which means this beam is orthogonal to another beam, but at the same wavelength.
Yeah.
So in this way, you can increase your spectrum efficiency.
Yeah, so it is like different, like in basic antenna, we have two polarizations.
But I think in wireless communication, people have done some research on OEM. What is OEM? Angular, orbit.
Moment.
Momentum.
Yes.
They are orthogonal to each other. You can use a single frequency, then you can transmit multiple channel signal.
Yeah, that is strange. So somehow the beam is curving in a very complex way.
Yes. But there is still a question about the isolation from different beam mode.
Oh, sure, yes.
Yeah.
Yes, any other comments or questions? Okay, if not, so then this closes this today's general lecture. We thank once again Professor Chi.
Okay, thank you, Professor Chi. Thank you, everyone.